So we will try to construct general solution to the Poisson equation. This is one of the questions that we posed during our lecture. So this is the Poisson equation. So we solve the scalar potential at point x given certain mass density rho. We will consider a bounded region. So let's draw it, and we denote them by gamma and denote the boundary here all the way through this and denote it by delta gamma. So now remember, this is a inhomogeneous equation, and we know that we need Green's function to solve this equation. For this case, you can use your well-known Coulomb's Green's function, but I will not going to write down explicitly the form of the Coulomb's Green's function. You can solve it by yourself. Rather, I will just use some schematic form of Green's function to write down the structure of the speech. So we know that the Green's function satisfies the following equation, that is del square g. So we denote the Green's function by g, is a function of 2 point x and x prime. So these 2 points are the 2 points inside the region. We pick any 2 points and denote by x and x equal to x square prime g x and x prime, and this is equal to the 3-dimensional Dirac delta. Also note that this is the Laplacian with respect to x. This is the Laplacian with respect to x prime. And again, to reiterate, these 2 points are within this bounded region. So now we apply Green's identity. So what is Green's identity? Identity. This you should be familiar with this from your vector calculus course. So given a region gamma and its boundary delta gamma, we have the following identity, that D3 x I I minus so we consider volume integral of these two function phi and psi and take this combination, and we can show that it's equal to the following surface integral over the boundary gamma. D of S is the element of the surface, or rather infinitesimal element, area element of the surface. Is function of x of phi in and this n denote the normal derivative to the surface. Now we substitute this phi as our scalar potential that we intended to solve for the Poisson equation. And this psi we choose to be the Green's function. Just to remind you, this is we intended to solve by solving the Poisson equation, and because it's a linear differential equation, so first usually we solve the Green function. The common one is the Coulomb's Green function. Please try to solve it by yourself. But we just doing a schematic analysis, so we just consider some G which satisfy this Green equation. And we choose one of these function phi inside the Green's identity as the scalar potential that we intended to solve, and another function psi as the Green function. And now we put this inside this Green's identity. Let's see what happens. First, look at the volume integral part. So now we have phi x. Now remember that this del square g satisfy the Green's function equation, and it is basically minus of delta function. Also, g delta prime square of phi. Now the scalar potential satisfy the Poisson equation. So we can replace this by 4 pi gn. So and because here there is a delta function, this will kill this integral, and this entire thing, the entire first term, this will simply give you minus phi of x, and you will have another term which is gamma, integral over gamma g x. Times the sum, this factor 4 pi gn. Let me write it here. Now, what about the other side of this equation? Let's analyze it. So we have a surface integral of gamma, which is ds x prime x prime. Now it will have n dot delta prime of g prime. This gives the normal derivative of the Green function at the boundary. Then another term is x. Okay, and this gives the normal derivative, and this is the bracket. This gives the normal derivative uh, of the scalar potential at the boundary. So now, if we equate these two equality, and then we can rearrange some of these terms. So we take some of these terms from the left hand side to right hand side, and finally we get the following. So let's write down the final answer. I at x is the scalar potential that we are trying to solve, equal to minus of x Prime. But we know that it satisfies Poisson equation, so we can replace it by that, as we have done in the previously. So here it is mentioned. So let's remove this and write it in the following way: minus 4 pi gn rho x prime. Then you have two terms coming from the surface integral d of f prime del g is the normal derivative and the other term is delta comma ds x. Again, this is a normal derivative of phi. So this is a generic form of the solution for the equation. So one important point to remember is that we know from uniqueness theorem that to get a unique solution to Poisson equation, either you specify phi or its normal derivative at the boundary. Don't need to specify both of them. We just need to specify one of them. And we just proved the uniqueness theorem in the previous video. But if you look at this form of the solution, it seems that it involves both phi and its normal derivative at the boundary. Remember, these quantities inside the surface integral we evaluated at the boundary, the region gamma. So this structure says you that apparently you have to specify both phi and its normal derivative, and it seems that it is in contradiction with the statement of uniqueness theorem. In fact, actually not, and we leave that for you to resolve. So take it as a puzzle and try to resolve this. Thank you for this.